Hello, this video will be explaining problem 15 in chapter 4. I think it's the elevator problem. Yeah, elevator problem. So, um, to start off, we'll draw a free body diagram. We have person on the elevator. Obviously, there's a force of gravity acting down on that person. And we have a normal force going up. Yeah, actually, this shouldn't be that tall. It should only be 3 dots tall. Because it tells you the normal force is 3/4 the uh, person's normal weight. So this normal force should be 3 squares if I have the force of gravity be 4 squares. So um, let's see, we have normal force. We need to make sure we label that the arrow here is positive. They don't give us the mass. We know that g is going to be 9.8 meters per second squared. The force of gravity, hopefully you guys know, is m times g. And if it says the normal force is 3/4 the person's normal weight, well, the weight is just another way of explaining the force of gravity acting on the person. So we can just say Fn equals 0.75 times mg. And we're trying to solve for A, the acceleration of the elevator. Now before we start, if the normal force is less than the person's normal weight, you should conceptually know that the elevator has to be going down. Okay? If you've ever been on a roller coaster, you should know that when you're going down the road, the roller coaster is going down off in the hill, that you don't feel the same amount of force coming from the seats. But when you're going up the hill, not the first hill that has the gear, because you may not feel it as easily on that, but when you're going up the hill, when you're no longer on the actual chain, so you go down the first hill, you go back up, then you should feel a greater force pushing from the seat onto you. The normal force is increasing because you're accelerating upward. Okay, a really good example with the downward example would be drop zone at Great America. If you've been on that, obviously, when you're going down, you don't feel the seat acting on the seat underneath you acting on you as you're moving downwards, because you're just falling due to Earth's gravity. There's not much friction in that case. There's some, but there isn't much. So conceptually, I want you guys to be able to understand that the acceleration should be negative when we get this answer. So let's go ahead and prove it mathematically. We know that the acceleration will be the sum of the forces divided by the mass. We need to make sure that we can explain that the sum of the forces will equal the normal force minus the force of gravity. And we could go ahead and just multiply the mass over, so we can say mass times acceleration equals the sum of the forces. And we know the sum of the forces equals the normal force minus the force of gravity. So we just take out the middle, say mass times acceleration will equal the normal force minus the force of gravity. Go ahead and rewrite that with an explanation of mass. So we have normal force would be 0.75 m times g minus m times g again, because that's just the force of gravity. You should see that the masses can cancel out. So you have A equals 0.75 g minus g. Oh, I forgot to put the parentheses. There you go. Now, that should be easily recognized as 0.75 g minus 1 g. So that would give you A equals a negative 0.25 g. We know the value for g is 9.8 meters per second squared. So you get A equals negative 2.5 meters per second squared. It's negative like we expected it to be. And 2.5 is about a quarter of the acceleration. The 10 obviously is a rounded number for the acceleration due to gravity, and we said a quarter of that, so 2.5 makes sense. Obviously, we rounded it up from 2.48, if I remember correctly. But there's your answer for problem number 15, chapter 4. Not much as far as challenge, other than if you got paused up by not knowing the mass. But whenever they don't give you a value, you can be pretty sure that it cancels out, or there's a way to find it. Okay, normally it cancels out. You'll see that with problem number 51. It's amazing how much stuff cancels out of that one, but that won't be for a few more videos.